and look at it should they need to. And I guess I'm not fully understanding what you're asking. So let me see if I can pull up mini project 2. Do you just not understand the instructions?
Like with the first mini project, the instructions, they were clear, but I didn't like understand how to like do the project because it was like hard.
Okay, well, first of all, I don't think that mini project 2 is going to be as challenging as the first one. Just from my perspective, students tend to struggle with that first one for some reason, more so than the others, despite the detailed instructions that were provided. But have you looked at the instructions for mini project 2? We did talk about it, I believe, at the end of last class about what the expectation was and what you needed to do. So I've tried to make them as clear as possible. It says clearly identify the data set you're using, because if I don't know what data set you're using, then I can't check your answers against that data set. And because I would have to try to guess at it. And then confident is because it's specifically related to confidence intervals, you have to use a quantitative variable. And you will actually use 2 different quantitative variables. You have part 1 and part 2. It's the same question or questions in part 1 and part 2, and that you're just doing it twice. And so then, because you're not given the summarized statistics, see, I'm not giving you the sample size or the sample mean or the sample standard deviation, anything like that, because all of you are using different data sets. And so the second question asks you to calculate the descriptive statistics, which you have learned how to do at the beginning of module 2 in Minitab. And then you're asked to construct a 95% confidence interval. I'm telling you to do 95% confidence. We're making the assumption that our population is normal. And then you have to calculate, just like we've been doing in class, the lower bound, the upper bound, and the error bound margin, and write the final conclusion. So I'm not asking you to do anything beyond what we have been doing in examples in class. And we did do a couple of examples, if you go back and look at the videos related to confidence intervals. We did do a couple of confidence intervals where you had to use the raw data. So that would be my suggestion. I think in this instance, I feel like, and maybe I'm wrong, the others can speak up, I feel like the instructions are pretty straightforward and are not anything that we haven't discussed or talked about or walked through in class together. So you might benefit from going back and watching the videos on confidence intervals. Okay. Does anybody else have questions related to the mini project? If you all do feel like the instructions are unclear or whatever, misleading, I can try to elaborate here in this venue. You basically do the same thing twice with 2 different quantitative variables. Okay, let me kind of tell you where we are then. Get us kind of back up to speed. Okay, this week, ideally, you've got to take the midterm exam. Okay, it's open. now. And you have until Saturday, October the 8th at 11:30 p.m. to take it. You're allotted 2 hours. I will tell you at the 2-hour mark, it is not going to go, excuse me, it is not going to cut you off. It will allow you to continue working, but it will send a notification to me that you took longer than 2 hours. I'm not worried about that if you take longer than 2 hours. The only scenario in which you would be locked out of the test is if you attempt to work beyond 11:30 p.m. on Saturday, October the 8th. Because at 11:30 p.m. on Saturday, October the 8th, it will close. It will lock you out. The door will be closed and you cannot work anymore. So that would be the only scenario, is if you attempt to work beyond 11:30 on Saturday night. Okay. You are allowed to have one 8.5 by 11 sheet of paper with handwritten notes front and back. Again, if you look at the study guide that I had attached to the week 7 announcements, at the very end of that document, you're going to find some very strong suggested formulas that you write down on that sheet. You can also have a writing utensil and scratch paper, because you may have to write data or write the information down on a sheet of paper, so and do the calculations. Okay, you will not be accessing Minitab during the midterm. If you need Minitab results, they are embedded, pasted onto the test, into the test question. Okay. The other thing is, you don't automatically get a grade once you submit the exam, because there are some questions that I have to go in and manually grade. I do try to monitor the submissions, excuse me, and grade those as quickly as I can. Okay, so you have the midterm that's due by Saturday, October the 8th at 11:30 p.m. Mini project 2 is due by Monday, which is the 10th. Okay, mini project 2 is due by Monday, which is the 10th. I also created its own paper and pencil. I didn't have time to get it entered into D2L, but there is a review sheet with an answer key, some of which is a video answer key, available for you to also review. So those are the two things you have, basically you have to complete this week. You have to complete the midterm by Saturday, October the 8th at 11:30 p.m. And mini project 2 is due by Monday the 10th at 11:30 p.m. Today, we're going to begin to look at module 3. Okay, we have to try to keep moving forward. And really our focus in module 3 and module 4 is going to be on what is called hypothesis testing. Hypothesis testing is one of the primary statistical analysis that we do. And basically what it boils down to is, with hypothesis testing, typically we've talked about how that research begins with a question. Well, typically when we pose a question, like what is the average age of a GHC student in fall 2022, if I were to pose that question, I probably somewhere in the back of my mind have an idea of what I want the answer to be. And so the process or the procedure of hypothesis testing allows me to test my proposed answer to the research question and to ultimately determine, is my proposed answer on target, valid, reasonable, based on the sample data that I have collected. You can kind of think about it like a court case. We do assume that a person is innocent until proven guilty. And so we assume that our hypothesis is true. And then we use the evidence from the sample data to ultimately determine kind of guilty or not guilty, sort of like a court case. We do talk about this process of hypothesis testing in Stat 1401. We look at it in relationship to a variety of tests. We're going to do that also in this course, but we're going to do other tests as well. Typically in Stat 1401, we only do what are called one mean Z or one mean t-test. We're also going to consider two means in this course. We also look at chi-square goodness of fit, but there are two other types of chi-square tests that we're going to consider. And we're also going to consider what are called non-parametric tests. And we'll talk more about what are non-parametric tests on Thursday. I do want to kind of go back and review the hypothesis testing process. And in that discussion that we're about to have, we're going to talk about hypotheses and p-values. We will talk about normality on Thursday. To facilitate our discussion, I posted yesterday morning a set of fill-in-the-blank notes that I used in the summer of 2020 when we were forced to go to remote learning at the last minute. And so I've posted those, and hopefully you maybe have printed them off, or you have it where you can maybe type the answers in on your screen, because this is kind of the process that is used for hypothesis testing. And so I want to walk through it together and make sure you recall or are familiar with that process, since it may have been a while since you've had Stat 1401. So the first step, and I'm using the fill in the blank notes. So the first step in the hypothesis testing process, of course, you would have your research question, and then you would state the two opposing hypotheses. Each time you conduct a hypothesis test, you're going to have two kind of opposing hypotheses. Again, sort of think about it as guilty and not guilty. The first of those two hypotheses is called the null hypothesis, and the symbol, we use a capital H for hypothesis, and it's a subscript of 0. You may or may not know the word null is kind of an old-fashioned or old word for 0, and so the symbol you'll see is H with a subscript of 0. And your hypothesis, really both of them, but the null hypothesis is a claim about a population parameter that is assumed to be true throughout the entire process. It must always contain equal in some form. Now, a couple of side notes there. Okay, remember we've talked about population parameters. Those are the measurements associated with the population, and primarily the ones we're going to focus on again in this course are going to be the mean. Okay, the population parameter that we primarily focus on in this course is going to be the mean, or possibly a proportion. There are, we don't discuss them in this course, but there are hypothesis tests that can be conducted on things like standard deviation or variance. When it says that it must always contain equal in some form, you really have three options for the mathematical symbol in the null hypothesis. It will either be flat out equal, it could be less than or equal, or it can be greater than or equal. Again, it has to contain equal in some form. The challenging part for most students is figuring out which symbol they need to use. And quite honestly, determining the symbol that needs to be used is going to be based solely upon the way the scenario is worded, or the way that I, as a researcher, express my hypothesis or proposed solution to the research question. Okay, so we'll take a look at that in a little bit in more detail. Okay, the second hypothesis is called the alternative. The symbol for alternative, it is the capital letter H, again for hypothesis, and I tend to use a lowercase a for alternative. There are some texts, just so you know, that use H with a subscript of 1. Again, I tend to use the A, and I know that that is how it is presented in the quiz and on the assignments throughout D2L. But some texts do use a subscript of 1. But it's a claim about the same population parameter that is the exact opposite of the null hypothesis, and it will never contain equal in any form. So it's about the same population parameter. Again, it's kind of like thinking guilty, not guilty. You have those two opposing hypotheses. And so the symbols that you might see in the alternative hypothesis, you would have not equal, greater than, or less than. And let me point out that you would always pair them. You would always pair equal and not equal together. You pair less than or equal with greater than, and you pair greater than or equal to with less than, because they are opposing, they're opposites of each other. Okay, and so they're always paired together in that manner. Okay, equal is always paired with not equal. Less than or equal is paired with greater than. And greater than or equal to is always paired with less than. The other piece that I want to point out here, and I made it in the statement, but again, I want you to kind of make sure that you understand what I'm saying, is that, again, you've got these two hypotheses. Again, thinking about it in the context of the court case, you know, in the United States, we assume that a person is innocent until proven guilty. So our initial assumption in court is that the person is innocent, unless there is enough evidence presented to prove otherwise. And so with hypothesis testing, we will assume that the null hypothesis, whatever it is, the null hypothesis is going to be true unless we have enough evidence to prove otherwise. The alternative hypothesis helps us out and gives us some additional information because it determines what we call the type of test. And the type of test is important, even using the technology of Minitab to do the calculations, because whether it is what we call a one-tail test or a two-tail test, affects the calculations. And that would be more obvious probably if we were doing hand calculations, but it does affect the calculations. And so we have to make sure that we identify to Minitab whether we have a one-tailed test or a two-tailed test. Okay, so a one-tailed test occurs if the alternative hypothesis contains either less than or greater than. And I'll try to give you some information here in just a minute so it'll make more sense to you maybe. A two-tailed test occurs if the alternative hypothesis contains not equal, because not equal implies that it could be less or it could be more. Again, the idea of a tail is we are relating this back to some type of distribution. Again, the most common one is the normal distribution. And so when we think about a normal distribution and we're trying to say that our mean or our average is greater than something, then that means we're going to have a point somewhere on the right-hand side where it gets to be way out of whack, gets to be too large, or it becomes what we call statistically significant. It's so different from the mean that it's not occurring just by chance. There's something going on. And so again, greater than, you would have an area or a region to the right at some point where it becomes statistically significant. So you only have that one region because you're only considering greater than. If you're considering less than, again, if you're thinking about the probability or the chance that something is less than the mean, you're going to be to the left of the mean. And again, at what point are you far enough away to say, oh, this is occurring because there's something going on. It's not just pure luck that I'm less than. And so again, you only have this one shaded region that's on the left side. Sometimes I think Minitab just uses the words one tail, but if your area is on the right, sometimes they'll refer to it as a right tail. Again, specifically emphasizing that it is greater than, because again, greater than is to the right. And for the other one, we would call it a left tail. Again, the shaded region being on the left because it is less than. So you might see those terms as well in other text. Two-tail, again, if you think about what not equal means it's just not the same. So it could be less, which means I would have a region to the left, or it could be greater, which means I would have an area to the right. So I actually have two regions, hence the term two tails. And again, I think as we go through this and think about it, it's going to make a little bit more sense to you. So just hang on. Kind of got to get through the steps first. Okay, so step one is to state the two opposing hypotheses. The null hypothesis will always and forever contain equal in some form and is assumed to be true throughout the process. The alternative hypothesis is the exact opposite of the null, and it determines what type test you have, one tail or two tail. And again, that's important because it affects the calculations. Second step is you need to collect your sample data. And if you have the raw data, you may have to actually calculate the descriptive statistics. That's what happens in reality. If I'm conducting research and I've asked the question like, what is the average age of a GHC student in fall 2022? and I propose my answer, maybe I say, well, I think the average age is 23. Well, then I'm going to go out and collect sample data. Now, again, I want to make sure that I use, an appropriate sampling technique that we talked about earlier in the semester. And then I'm going to organize that data, maybe into a table, and calculate the descriptive statistics. Primarily, I need the mean and the standard deviation. Now, I could calculate all the other things as well, the mean, the median, the mode, the range, standard deviation, but I primarily need the mean and the standard deviation. If in our case, because I don't have a lot of time for you to go out and collect data every time we do a question, you're going to be given the scenario. And so you have to identify the given information or the given summary statistics. Just like in the questions for the confidence intervals, you were given typically the sample mean, the population or the sample standard deviation, the sample size. Okay. In the scenarios that you're going to be presented as the problems or examples for hypothesis testing, you'll be able to identify that information. The information that you need, okay, you may say, well, Ms. Rawson, what information do I need? The information needed depends upon which test or which, I don't know what that's supposed to be there. Depends on which test is being conducted. Are you going to be doing a one mean Z, a one mean T? Are you doing ANOVA? Are you doing chi-square? So it depends upon which test is going to be conducted. And I don't know what I don't know what this other blank is. Maybe I just got carried away typing. Okay, so you've got to gather, basically you got to gather the evidence. And the evidence that you gather is going to depend upon which test. So step 3 is to determine which, again, I got an extra statement in there, which test to conduct. Okay, which test to conduct. And I want to focus on 2 of them this morning that we do in 1401, and we're going to review in this course probably next week. One of probably the most popular, one of the ones that's used most often, is you can actually call it a one mean Z test. A one mean Z test is used when we have quantitative data. N, which is our sample size, is greater than or equal to 30, so that you have a large sample. The population standard deviation is known, and the one mean Z test is related or connected to the normal distribution that we've been talking about. If you think about it, for a Z interval, for the confidence interval Z, we had to have the population standard deviation, and it was connected to the normal distribution. So it's kind of that same idea. A one mean Z hypothesis test is going to have a large sample, meaning it's typically greater than or equal to 30, or we know that the distribution is normal, and we know the population standard deviation. So typically in the scenario, when you're reading through the problem, okay, it's going to give you several things. It's going to give you the population mean, which is included in the hypothesis. It's going to give you the population standard deviation, which is sigma. Then you have your evidence. You have your sample mean, which is X bar. You have your sample size, which is N. And you have what is called the level of significance. And we'll talk about what that is in just a minute, which is represented by the Greek letter alpha, the one that looks like a little fish. That's the Greek letter alpha. We also will review a one mean t-test. Okay, one mean t-test also applies to quantitative data. Your sample size is likely less than 30, or what we consider small. The sample standard deviation is, oh wait, I said that wrong. The way I have it worded. Okay, the population standard deviation is not known or given. What you are typically given is the sample standard deviation. And this one is related to the student's t-distribution. Again, connect it back to the confidence interval for t as in tiger. Again, we typically had a sample less than 30, or we knew the distribution was normally distributed, but we were given the sample standard deviation instead of the population. And again, students t was initially established or created to deal with those smaller samples. So it's kind of that same idea if you want to make that connection back to z interval and t interval. If you have a one mean t-test, you still need the population mean, which will be given in the scenario and is included in the hypothesis. You have the sample standard deviation. You're given the sample mean, the sample size, and again, that level of significance, which is represented by the Greek letter alpha. We will additionally talk about, and when we get there, I'll kind of give you the same kind of list, two mean t-test. We will also talk about ANOVA, or analysis of variance, and we will also do chi-square, goodness of fit, as well as two other chi-squared. Okay, so I'm just going to kind of give you a couple things. Chi-square goodness of fit is one of the few tests in statistics that deals with qualitative data. Remember, we've talked about sometimes with qualitative data, there's not as much analysis that can be done because it's words. But one of the few that we can do is called chi-square goodness of fit. So it deals with qualitative data, and we'll be focusing more on it in Module 4. Analysis of variance, or abbreviated ANOVA, is actually kind of a combination because it is quantitative data. So we have numbers sorted by a qualitative variable. And actually, this particular topic in this course is the last part of Module 3. A good example here might be if you want to look at maybe GPAs sorted by pathways or majors. You know, do business majors tend to have higher averages than, say, nursing majors? But you can take a quantitative variable like GPA and sort it into a category by qualitative variable. This one is a good one for like if maybe you're a regional manager for, say, McDonald's, and you can look at the drive-through wait times at all the various McDonald's locations in your region or within a particular city, you know, to see is one better than the other. You know, is there something that they're doing that could benefit the other locations? So again, that's analysis of variance, and we actually will look at that at the end of Module 3. And then correlation, we get into what's called bivariate. You have two variables at the same time. They're both quantitative. So you have bivariate quantitative data, and that gets into correlation, which leads us also into regression. And that we'll get to talk about more in Module 4. Now this says using the free website. It's supposed to be using Minitab, and I thought I changed that, but maybe not. Okay, so using app.minitab.com. We're going to calculate and record what's called the test statistic and corresponding p-value. Okay, so in step 2, you kind of have gathered the evidence. Step 3 is kind of like you're going to be deciding how to present the evidence and all that. And then step 4 is you're going to present it. So we take the evidence, we present it, and in statistics, from a hypothesis testing standpoint, our results are a test statistic with a corresponding p-value. Now that may be some terms that you are not familiar with, so let me see if I can explain those a little bit. A p-value is a probability value. Okay, kind of makes sense. P, first letter of probability is P, so it's a p-value. The p-value represents the probability of getting the same test statistic over and over and over again if the null hypothesis is actually true. Okay, it's the probability of getting the same test statistic over and over and over and over again if the null hypothesis is true, which means results from another random sample will be as extreme or more extreme than the results of the given sample. Again, the idea is we're thinking about, sometimes you can look at the data and you go, well, duh, Miss Ralston, yeah, that's bigger. Or yes, that's smaller. But the question is it big enough or is it small enough to say, yeah, there's something going on. This value did not just occur by chance. The term for that is being statistically significant. We say, is our data or is our test statistic statistically significant? That's a lot of words. Okay, is the test statistic, the result of our evidence, Is it statistically significant? Is it different enough from the mean or from the data to conclude that there's something else going on besides just pure chance? And that's kind, I mean, that's kind of a hard thing to wrap your head around. The test statistic is, again, based on which of the tests you calculate. Okay. So once you've got your evidence and the evidence has been presented, then you have to make a decision. And that there's two options. Okay, you're either going to reject the null hypothesis, that's one option, or you're going to fail to reject the null hypothesis by comparing the p-value to the level of significance. And I realize I haven't explained level of significance yet, so hang on and I will. Okay, notice that our decisions are, again, based on the null hypothesis. Because remember, at the beginning, we've assumed the null hypothesis is true. Just like we've assumed a person is innocent until proven guilty. So we have assumed our null hypothesis is true unless we prove otherwise. The other thing that I want to point out is the way that these things are worded. The option is we reject the null hypothesis. Okay, rejecting the null hypothesis implies that the null hypothesis is false or wrong. So this would be like saying that the person is guilty, because we reject the assumption that they're innocent. So if you reject the null, that's like saying the person is guilty, okay, and our original assumption is wrong, not valid, not reasonable. The other piece, the other one here, notice it's fail to reject the null hypothesis. Notice that we do not, should not ever use the phrase that we accept the null hypothesis. Okay. Again, think about it in terms of a court case. We come back and we report they're either guilty or not guilty. We do not say they're innocent. Okay. Fail to reject is the equivalent of saying they're not guilty based on the evidence that was presented. There was not enough evidence to convince me that they did the crime. But I'm not saying they're totally innocent. That phrase, not guilty, could still imply that they might have done it, but there wasn't enough evidence. So the deal is, we say fail to reject the null based on the evidence. Based on the evidence, I don't have enough to prove that it's wrong. But if I collected a different sample or collected more data, I might come to a different conclusion. So we never truly accept, prove beyond a shadow of a doubt that the null hypothesis is true. Okay, so be careful of those wordings. I'll just flat out tell you, it crawls Miss Ralston's skin if someone says accept the null hypothesis, because that is statistically incorrect and very, very wrong. So how do you decide? How do I decide whether I should reject the null hypothesis or fail to reject the null hypothesis. That is based on a comparison of the p-value, which is related to the test statistic, and the level of significance. Okay, so I'm going to give you the rules first. If the p-value is greater than hold on, I got to say it right. I got it backwards. Okay, if the p-value is less than or equal to the level of significance, then you reject the null hypothesis. And you'll see it written this way. The p is less than or equal to alpha. We reject the null. If the p-value is greater than the level of significance, then you fail to reject the null hypothesis. So if p is greater than alpha, you fail to reject the null. Okay, then the last step is you got to kind of tie it all together, sort of like the jury comes back and reports back to the judge. You got to write a final conclusion in terms of the true. It really should be in terms of the null hypothesis, but students tend to get confused with that. So it's easier to say, write a final conclusion in terms of the true hypothesis, including the level of significance. And then I need to go and I need to explain level of significance to you because I forgot to do that. Okay. At the end of module 2, we were talking about confidence intervals. And you had a confidence level, and the confidence level is kind of like the probability that you were correct, that the population mean falls within that given interval, so that you are correct, that you have correctly selected an interval. And we tended to use most commonly 90%, 95%, or 99%. Again, confidence levels are usually presented as percentages, but they could also be presented as decimals or whatever. So we've talked about confidence levels, and again, that's how confident you are in your solution. And again, it's the probability that you are correct. Well, if there is a probability that we're correct, there also has to be that chance or the probability that I'm incorrect or that I'm wrong. The probability that I am incorrect is called the significance level or the level of significance. It's actually represented by the Greek letter alpha. Formally, it says it's the probability of a type 2 error, but we really haven't talked about type 2 errors. Again, it's basically that you come to the wrong conclusion. Well, if both of these are really probabilities, and we know that probabilities have to total to 100%, if I'm 90% confident that I'm correct, that would imply that I'm 10%, there's a 10% chance that I'm incorrect. But typically with significance level, you see them written as a decimal So 10% would be 0.10 as a decimal. If I am 95% confident that I'm correct, that means there is a 5% significance level that I am incorrect. And as a decimal, that is 0.05. If there is a 99% chance, or I'm 99% confident that I'm correct, then there is a 1% chance that I'm incorrect, which written as a decimal is 0.01. And again, typically your significant levels are presented as decimals rather than percentages. It's not wrong to write it as a percentage, but again, it's typically presented as a decimal. And so you have that connection between, how confident are you that you're correct, or how significantly different, what's the chance that you're going to be incorrect. And again, that gets into the idea that it's statistically significant. What's the chance that it's going to occur again from another sample? Again, that's your p-value. Okay, so that's level of significance. So this gives you kind of that step-by-step process that we go through to conduct a hypothesis test. Now, a lot of it has to do with the phrasing. Okay, so do you have questions about the process? I know we haven't done the process, and so sometimes students don't really have a question until we start getting into the process. Hopefully, if you've taken Stat 1401 recently, it'll look familiar to you. Okay, I think that I removed the examples, and I really don't want to get into the examples today. Okay, we may try to do that on Wednesday, or excuse me, on Thursday. But let's go ahead, since we have about 15 minutes, and take a look at, because the other thing that's different is we're going to take a look at parametric and non-parametric test. Okay, non-parametric is probably a brand new topic that you have not seen before. And this PowerPoint that I'm about to kind of walk through with you is in the D2L section. I added it yesterday. Okay. But I want to talk about the difference between parametric and non-parametric test. Again, pretty much everything we do in Stat 1401 is a parametric test. So non-parametric is very new. It's not something you've seen before. So if we compare the two, what's the difference? And why do we need both of them? So we're going to compare parametric to non-parametric. First of all, a parametric test really is only used with quantitative data. Okay, so it's numbers, which again is typically what we prefer. If at all possible, we prefer to deal with numbers as opposed to words. So parametric tests only apply to quantitative data, typically data that's at either the interval or ratio level. For a parametric test, we do have to make several assumptions about the data. The primary assumption that we make is that the data is derived or is taken from a normal distribution. That variable has a normal distribution, and that there are no outliers. Parametric test is best if there are no outliers. And we also assume, if we're looking at more than one data set, that each data set has the same variance, which would then also imply it has the same standard deviation, so that they have a similar shape to one another if you're looking at more than one data set at a time. So that's three pretty big assumptions: that we have a normal distribution, there are no outliers, and equal variances. A parametric test is a test about the means. We look at the mean of the variable, the mean age, the mean fat content, the mean number of siblings a person has, the mean number of credit hours, the mean GPA. Okay, so the parametric tests are about the population parameter, specifically the mean. For parametric test, having a large sample is best. Again, that's typically a sample size of 30 or more, because then that allows us to assume the normal distribution under the central limit theorem. And the other thing is that a parametric test has more statistical, quote, power. Okay, to me, what that means is that the test is more likely to detect the significant differences when they actually truly exist. It's basically saying it's going to hit the target more times. It's more likely to hit the target than a non-parametric. So it has more statistical power. For a non-parametric test, we can still use quantitative data, but we can also use ranked data or qualitative data. Oftentimes for non-parametric, we're looking at things that are maybe at the nominal or ordinal level. Okay, so that typically means they're going to be qualitative. But we can also still use a non-parametric on quantitative, and we'll talk about when that might be a good time, when is a good time to do that in just a minute. The nice thing about a non-parametric, and I'm hung up, looks like, of course I am. Let me go back and share my screen again. It gets hung up, you know. Oh, come on now, be nice. Okay, now let me get back over here and share the screen again. Okay, so a non-parametric, one of the kind of the good things about a non-parametric is that it does not require you to have a normal distribution. And oftentimes it's not going to be a normal distribution. Non-parametrics are sometimes called a distribution-free test because you don't have to know anything about the distribution. It could be skewed to the left, skewed to the right. It could be a uniform distribution. It could be exponential, and you can still run a non-parametric test. It also allows for outliers, and we don't have to assume equal variances. We don't even have to know the variances for the distributions to use a non-parametric test. One of the differences, again, another difference between parametric and non-parametric is that non-parametric test the median rather than the means. And if you think about it, that's one reason why outliers would be acceptable for a non-parametric. Remember that outliers can influence your mean or your average. It can cause it to be inflated or deflated. And so if I'm testing the median, which is simply the middle value that doesn't really involve a major calculation, then those outliers are not going to affect it. And then finally, a non-parametric does allow for a small sample size, but it has less statistical power. It may not be as accurate, so to speak, as a parametric test. And there are some arguments about, well, why don't we just use non-parametric all the time? Well, again, because they're not as powerful. And so that you have to weigh, make that decision based on what kind of data do you have. Do you have a data set that has a lot of outliers? And if you do, then maybe you want to do a non-parametric test as opposed to a parametric. Again, the parametric are actually, in a sense, that idea of having more power is that they're a little bit more accurate. So again, how do you decide which one to choose? Well, again, you have to think about what kind of data you have and how your data set is set up. Do you have quantitative data that's at the interval or ratio level? Does the mean accurately represent the center of the distribution, which typically is going to imply perhaps you have no outliers, or the outliers could be removed. Does the mean accurately represent that measure of center? And then do you have a large sample, or do you know that your distribution is approximately normal? For non-parametric, again, you could have quantitative data or qualitative data that's typically at the nominal or ordinal level. You can have qualitative data, and I got that backwards. Median, again, does the median more accurately represent the center of the distribution? And again, that's where you got to think about, do you have a lot of outliers? And are those outliers influencing that mean or the average, so that you really should use the median? And you definitely can use non-parametric if you have a small sample, or you have an unknown or a non-normal, it's kind of a weird word, non-normal distribution. Because again, non-parametric is often referred to as distribution free. It doesn't, it doesn't assume anything about the distribution. So every parametric test has an equivalent non-parametric test. And so again, as we go through modules 3 and 4, we're going to look at the parametric test, but we're also going to look at its non-parametric equivalent. And so this is how some of them kind of pair together. Okay, you have a 2-sample t-test, and the non-parametric test is called the Mann-Whitney. You have a 2-sample paired t-test. Its non-parametric equivalent is Wilcoxon. For one-way ANOVA, the equivalent in non-parametric is Kruskal-Wallis. And then for the Pearson correlation coefficient, you have the non-parametric Spearman rank. Now again, those are not all of the non-parametric tests that exist. Those are not all the parametric ones that exist. Okay, those are some of the ones that we're going to be focusing on throughout module 3 and module 4. I see a typo there too. We're also going to consider in module 3 a couple of what we call post hoc tests. Once you've completed your initial analysis and you want to maybe go 1 step further or 2 steps further, there are some additional tests that we can do. The 2 that we're going to consider are called Cohen's D and 2K's test. We'll be looking at those. 2K's is related to analysis of variance, and Cohen's D, I believe, is our t-test. So again, it's kind of a little bit something new that you haven't seen before, but we're going to be talking about some of those non-parametric tests. Okay, so do you have any last minute questions? Again, maybe put this on the back shelf. until after you get through the midterm, which is due by Saturday, the October the 8th, and you get through mini project 2, which is due on Monday, October the 10th. And then we'll pick back up on Thursday. We're going to talk about one of the assumptions we make with parametric test is that we have a normal distribution. Well, how do we decide if we have a normal distribution or not? And there is a test for normality, or a normality test. There's actually a variety of them. We're only going to look at one. And so we're going to talk on Thursday, how to do that. And then we may also begin getting into the one mean Z and the one mean T test that hopefully will be a quick review for you guys. So question.